So, hi everyone. Let's wait for another 2 to 3 minutes. If others join, then we'll start the session. And kindly mute your mics if possible. Like someone's mic is turned on. So let's start today's session. Just a second. So let us start today's session. Just a second. Let me connect my iPad. Give me a moment. I guess everyone can see my screen. Just a second. Turn it on. So it's visible. So welcome everyone to today's session of this problem solving session of week number 5 of this course titled as Sensors and Actuators. My name is Shomnath Bhattacharjee. I am a PhD student in the Department of Electrical Engineering, IIT Jodhpur, and I am working towards development of flexible and organic transistors for neuromorphic computing applications. Previously, I have done my BSc in physics and MSc in electronics, and the class schedule is generally on Sundays from 6 to 8. But for the next 2 weeks, I'll reschedule the classes, and you all will get notification through the NPTEL forum and everything. So, like you will also get notification directly as well. So I might take a class within a few days, like 3 4 days, and the next class will be rescheduled to the next week. So just a second. So let's start with today's session. So this is a, as you all know, that this is a 12-week course, and in this course we have completed one third of the course up until now. So in this week, we'll the course through the course layout. So this part of the week is this part of the course is known as like silicon as a substrate, COMSOL multiphysics, and gas sensor demonstration. Out of which I'll omit the gas sensor demonstration because in the previous class I've already discussed about Arduino and how to interface different sensors, actuators, and these kind of a things. And because of that, I'm not going into details of this gas sensor demonstration and everything, although I'll like discuss a bit of that, but if anybody requires it, I can discuss it further. And we'll mainly discuss on the silicon as a substrate, different like measurement techniques, like also like PVD techniques as well, and also the COMSOL multiphysics. So as you guys can see, so like in this one, just a second, let me change the colors. So yeah, so in this week, we'll learn about the basics of silicon wafers, the orientation, silicon dioxide formation, thermal evaporation, thermal oxidation, and these kind of a things. And apart from that, we'll learn about how to measure the thickness of this deposited oxide layers and everything, like the silicon dioxide or something, and how do we measure the thickness, and what are the different techniques, and in which case we should use a separate technique, or we should use a different technique and everything. And finally, we'll learn about the COMSOL multiphysics platform, and how to simulate our, like before fabricating the like the sensor itself, how do we like simulate it, and what is the need of this kind of a simulation and everything. So I'm not going into that part of the Arduino integration of MQ3, that one, so the gas sensor and everything. So if anybody has any question, you can ask me, and I can also discuss on that as well. Yeah, just a second. So let's start with the basic things. Let's start with that. So a silicon wafer is like as already described in the videos and everything. So at first, silicon crystal is formed through silicon ingots and everything, and after that they are sliced and then polished, and based on that, so basically silicon wafers can be of two different types, like if based on the polishing and the etching part and those things. So based on the polishing, we can say there are two different types of things. So that first one is silicon single side polished silicon wafer. Another one is double side polished silicon wafer. So based on your requirements and everything, you would have a polished side or a rougher side. So based on that, so if you check it on like under a light or something, you can easily see which side is a polished one or not. So from here you can see this is a polished one, and on top of that, so these are called the basic silicon wafers and everything. So in this single side one is a polished side and another is a rougher side. But in case of a double side polished one, we have polished plus polished side. Now, so this is a basic thing that a silicon wafer is like that. And in the videos there was a demo silicon wafer and everything. So professor handled with his bare hands and everything. But inside what is like inside a clean room and everything, we need to handle it with tweezers if it's a smaller one. So in basically we don't use a huge or a large large size silicon wafer like a 4 inch or a 2 inch wafer. We don't use it like that. What we generally do is that we cut a small piece of it. So let sorry, just a second. So let's say we have a larger silicon like this. Out of that, what we do is that we cut a piece like this, and we just generally use that piece to fabricate the devices. So in a R&D lab and everything, this is the usual practice and everything. But in case of like larger industries and everything, so what they can do is that they can fabricate sensors and everything onto directly the whole silicon wafer. So it may be a 8 inch wafer or a 4 inch wafer or something like that, and they can fabricate directly on top of that. Now, but in our case what we generally do is that because it's a very costly thing, so we generally cut it cut in slices and everything, and based on that we use a very smaller one, because inside this silicon wafer or something like that, we can fabricate many sensors as well. So this is like this. So let's assume this as a 2 inch or a 4 inch wafer or something like that. Okay. So now, based on this, the crystal orientation of these silicons, so there can be several different kinds of silicon wafers. So this is a P-type silicon wafer with 111. Now, what is 111? So these are the Miller indices, and based on that, so there's a very basic technique to understand how can we determine um which Miller indices does the wafer have. So we have a primary flat. This is known as a primary flat, and it doesn't have any kind of a secondary flat, or there is no cutout portions of the wafer or something like that. So like it can stay directly flat on top of this surface or something. So that's why it is called a primary flat, and based on this primary flat, with a single primary flat, the it is always an p-type 111 silicon wafer. Now, after this primary flats and everything, so we also have different kind of flats. So when we need an n-type silicon wafer with 111, we have a different kind of a thing. So with the primary flat itself, we have another flat. Sorry, just a second. We have a flat like this. So this is known as the secondary flat. Okay, so this is known as a secondary flat. So what is a secondary flat? Secondary flat is anything apart from the primary flat. So we have a primary cutout of our wafer, and then we have another cutout of this wafer as well. So that is known as a secondary flat. For N type, there is a single, you can see. So there's an angle difference of 45 degree, and for N type, we have a 45 degree angle variation. Sorry. 45 degree, and similarly for the next one is a p-type 100, and in this case this is also the primary flat of yours. There's a very smaller flat, I guess everyone can see this. So there's a very smaller flat. This is your secondary flat as well, and you can see, so this angle is nothing but 90 degree. So for p-type there is a 90 degree flat, and similarly in this case you can see is the primary flat and there's a secondary flat, and from this you can say this is the 180 degree C flat. 180, sorry, 180 degree, a 180 degree difference between these. Just a second, let me. Yeah, so there's a 1 degree difference. So based on this standard procedure and everything, so based on the position of your flat on the silicon wafer and everything, so you can decide whichever which crystal orientation does the wafer have. And as the total ingot is in a single mirror indices form. So when we cut it, there's just a second. There's slices of that, and every wafer coming out of that ingot is directly of that. So a complete ingot of P type 111 will by slicing it based on a single one. Can we just a second? There's a question. So in fabricated sensor, can we Arduino or any deck for testing? Um, can you turn on your mic and ask the question actually? So I didn't got the question.
Good evening, sir.
Yeah.
I am Bhavani Shankar from Annamalai University, sir. I
Hmm.
am currently doing research in micro sensors, sir. In NPTEL portal, I enrolled this course for my research objective.
Hmm.
In this lecture, in a lab training section, professor says using Arduino Duo board for testing the gas sensor model.
Hmm.
But I haven't query mean we fabricate the sensors in laboratory,
Hmm.
then the fabricated sensor directly test by using Arduino Duo board
Yeah.
or
Yeah.
some
Yeah. Yeah. Yes. 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 Obviously, but there are some catches as well. So, like, can you describe your sensor or something like that? So it will be better to answer. It will be specific towards your.
sir. I am designing the flexible pressure sensor, sir.
Hmm.
So I purchase some basic models for pressure sensors
Hmm.
in the market. I can do some basic sensitivity selectivity test from the theory.
Is it a piezo resistive or piezo electric one?
Piezo resistive, sir,
Okay.
because it's
Yeah.
available in market and easily
Hmm.
to get some
No, no,
basic
no.
calculations.
No, no, no. I am asking about what you have fabricated. So is it a
I am
piezoresistive?
fabricating piezo resistive, sir,
Okay, okay, that's fine. Yeah, continue.
so that I am designed for this. So any data acquisition system specifically to increase the data points in the system because to get more accuracy.
Okay, so you are asking about that. So there is I don't work entirely on the piezoelectric or the piezoresistive domain or something like that. But in my lab, people also work in that domain. So what they actually do is for to getting a higher number of data and everything. So they use a linear actuator, and based on that, so it is something like that. So maybe I can show you. So if let's say it's your sensor and it's a linear actuator, so what they do is that it's completely mechanical, and based on that they touch it continuously
Yes,
with
sir.
a specific pressure or force, and with a specific time delay and everything. So based on that they generate the data, and that gives you a very long time data and everything, so a longer number of data and everything. And that is also what I think is very low cost as well. So like it depends on your budget and everything, but it was around 8,000 to 10,000 nearly.
Okay, sir.
Yeah, so
Thank you, sir.
that's a cheaper one, so you can use that for your purpose.
Yes, sir.
For
Thank you, sir.
and In my lab as well, people also what do you people also use Arduino and also ESP32 to interact that sensor with directly to your mobile phone and get the data and everything. So they work on different domains and everything. So they also are working on UV sensors and these things. So they are also interfacing these sensors directly with the phone and through Arduino and ESP32. You can
Thank you,
use
sir.
that. Yeah, you can
Yes,
you can
thanks.
check out Flame Research Group, IIT Jodhpur. So maybe you can get some ideas from their paper or something like that.
IIT Jodhpur, sir.
Yeah, IIT Jodhpur Flame Research Group, FLAME. You can check
Thank you
that
very much,
out.
sir.
Yeah. Okay, that's fine. So this is the what I was saying is this is the basic crystal orientations and everything. So based on that we can choose whichever silicon crystal to use. And why is it important? Because in many specific cases, so like while etching, so there are specific etchants which will etch away, let's say that's just it's just a like example, but let's say you have a specific etchant, and this etchant works based on 111, but it works very low on this. Okay, it's very low but very high on this. So let's say you have a structure with 111 and 100 silicons, and you just put the agent on all the surfaces and all the areas and everything. What will happen is that, let's say you have a structure like this, okay, and this one was 111, this one was 100, and this one was also 100. So what will happen is that with time this one will be etched away more. There will be like obviously these areas will also get etched, but this will be small and this one will be much bigger one. So based on these kind of a things, you need the specific crystal orientation for your like for your use case and everything. So let's move on to the next one. Yeah, so now after like there are several PVD techniques to use. So let's first go to this one, I guess. Let's first move on to this one. So there are several PVD techniques. So the first one is that obviously you can use the process thermal oxidation. So what it does is that it generates silicon dioxide directly from the silicon wafer, and it also erases away the silicon wafer, but it increases the total like total length and everything, and silicon dioxide is directly deposited on top of this silicon wafer and everything. Okay, so apart from that silicon basic thermal oxidation and everything, what you can do is that you can use any kind of physical vapor deposition techniques. So there are several physical vapor deposition techniques like e-beam deposition, as I have already discussed very but that was in a very basic manner or something, so that's why I am discussing it more. So e-beam deposition, there can be thermal deposition techniques, and there can be sputtering deposition techniques. So I have already discussed sputtering in a more described manner and everything. So in sputtering deposition, the basic principle was that we in a very plasma environment and everything, in a very high pressure and environment, what we were doing is that we are sputtering a specific kind of a ion on directly onto your material, and it was getting directly sputtered onto the target material. So this was the basic thing about sputtering, and this gives you the most smooth film and everything. So that was sputtering. Apart from that, we have another two very simple processes and very low cost processes as well. So that are thermal deposition also. I have mistakenly put it here. So let's first remove this. There is no magnetic field in this. Or let's remove this one, I guess. Okay. There is a magnetic field. Just a second. Let me correct it. There's no E-beam. So this is called not through this. This is directly connected through this. Okay. And this is called a boat. This is a heat filament. And everything is very similar to this. Let me not do this maybe. So, I have put the wrong image here, but both are exactly kind of similar. So, what happens in a thermal evaporation is that we have a source material here. I guess just a second. So, this is our source material here. The source material is put inside a pot that have a very high melting temperature. So, if this has a melting temperature of let's say X degrees C, this have a melting temperature of y degree C, and always y degree C will be much higher than the x degree C. So there is little to no, like there is literally no melting of the boat itself. Okay, so that's the major matter. So you have a heat filament inside that, and sorry, not a heat filament, let me write it correctly. So this is a resistive filament. So through this resistive filament, the boat is heated, and based on that, this source material is turned into a vapor, and this vapor is directly put this vapor and everything occurs inside a chamber. So this chamber is called a evaporation chamber, and inside this chamber there is a very high vacuum of 10 to the power minus 6 torr nearly. So inside this 10 to the minus 6 torr and everything, with this high vacuum and everything, what happens inside this chamber is that this source material gets converted onto like vapor, and this vapor will travel directly because it's in a plasma condition and everything. What happens is that this vapor travels directly, and there's like if there's a mask or there's something, so it can be there. But apart from that, there is there's this wafers, or you can say the sample, and on top of that sample the material gets directly deposited. So it's getting deposited physically, that's why it's called a physical vapor deposition. In case of sputtering as well, the process was same. Now for the case of this e-beam deposition, what happens is that everything is exactly similar, but in case of this there's a magnetic accelerator and magnetic field application. Okay, so based on this magnetic field, what happens is that e-beam is directly directed on top of this source, and inside that board, there's a source, and the source gets heated up, and based on that the vapor is formed again, and everything is exactly same. So why do we need a separate technique like e-beam? So to deposition of silicon dioxide or something like that, that has a very high melting temperature. So like silicon dioxide, it has a very high melting temperature. So these kind of materials will be easily deposited utilizing EVM deposition and everything. Apart from that, we can also use a normal like deposition technique. So a normal deposition technique, you can see directly that because you are just heating it up with a very high voltage and these kind of a things. So it's a more cheaper option, and for different materials we'll use that one. But for silicon dioxide and these kind of a thing, these kind of materials which have a very high melting temperature and everything, so like we'll use the EVM deposition. Now as we have already discussed about this deposition techniques and everything, now the main case is, let's just move here. So based on this, so based on our discussion so far, we know that we have deposited like silicon dioxide on top of the wafer itself. So previously in thermal oxidation, if I can say, so if this was your silicon, your new silicon wafer will, just a second, your new silicon wafer would be like this. So the top part will be silicon dioxide completely, and the bottom part will be silicon. So there is a reduction of this silicon like amount of silicon. But in case of these kind of a deposition, PVD depositions, if this is your silicon dioxide will be directly deposited on top of this, and there will be no reduction of the silicon itself. So there's a physical way to directly deposit on top of that. Uh, just a second. There's a question. Why spinning is necessary? Yeah, so spinning is very necessary because, like, let's say, do I have a space? No. Um, let's draw it here maybe. So let's check here, right? So let's say you have a wafer like this, and this is your, like, from the bottom you are seeing this. So this is a kind of a top view of your material or something. So let's say your wafer was here, as your total vapor area is here. If your substrate, it's within the range of your total vapor, there will be equal distribution of the material and everything, so you will have a very uniform film and everything, okay. But there might be some problems with the vapor, there might be some problems with the material itself, there might be some problems with the surface itself and everything. So based on that, we need a uniform rotation of that, because let's say based on the vapor and everything, so if your wafer is, so let's first understand that you are not using a single wafer at a time, so you are using multiple wafers and multiple like small pieces of chunks of wafers inside this rotation chamber and everything, okay. So if let's say your vapor is coming up to this point and it's on this way and everything, so what will happen is that your silicon dioxide will be only deposited onto this area, there will be a very small amount of deposition in this area as well, but outside that there will be no deposition. So if you are using a rotation, so if your sample is rotating continuously, what will happen is that without like irrespective of your like the vapor location or the vapor area and everything, there will be a uniform deposition throughout this sample. So you need a basic rotation of this sample itself. Similarly to that, there are several different cases as well. So based on the different materials you are using, you might also heat this as well. So there might be a heater, so heat the wafer first, so that the physical vapor or something like that, when it touches that, it will directly get stuck onto that because of the heat there. So there might be a specific heating of this. This heat is a very smaller one, a very small heat, but there might be some, and for like flexible and there. Um in which case, with the heating or with the rotation you were saying? Why? Why there? Like there will be a rotation. Like with the rotation, why you are thinking that there would be an uneven coating or something like that?
Sir,
You can turn
if
on your mic
the
and yeah.
if the coating is done at one part in one rotation,
Hmm.
and
No, no,
the
it's not a single rotation or a double rotation. So it's continuously rotating, right?
okay,
If
and
you
then
are,
it change.
let's say in some of the cases as well, like for my research as well, what I have done sometime is that I don't turn on the rotation itself, because in general if I use like I am fabricating a very small number of sensors or something like that, so what I do is that I only put this inside this range, only directly inside this range. So what happens with that is that there will be anyways a uniform deposition and everything. So but if you have a very huge number of samples and everything, and there might be a possibility of an uneven like coating or something like that, so that's why we need the rotation, we need the heat. And as I am working in a flexible domain and everything, we don't generally need a heat like additional heat or something like that, so we don't put any kind of heat there as well. Yeah. So what I was saying was that so we have directly deposited this, right? Now we need to know this thickness, or let's say this thickness. So how do we get to know this thickness, right? How to know the thickness of this SiO2? So there's a thing called crystal monitor. So uh, let me change the color. Quartz crystal monitor. So a quartz crystal monitor measures the thickness of this, but even if you need like verification if the thickness is correct or not, or even in some cases as well, so like it's completely like inside the chamber itself. So sometimes there's a problem with the quartz crystal monitor, and there is also a matter of health of this quartz crystal monitor. So there's certain rules and everything. So like if your quartz crystal monitor has a health less than 75%, there's a error percentage of the measurement and everything. And if you need a very perfect measurement and everything, so you need to cross verify with several different techniques. So these techniques are like ellipsometer. So ellipsometer, what ellipsometer does is that it measures the thickness of this deposited layer. Let me write it down first. So what it does is that it measures the thickness of the deposited layer through optical or non-contact means. Okay. So we are measuring it through an optical or non-contact means. So apart from that, there are several other techniques as well. So based on the constructive interference, simplified as the color. So based on the color of a specific certain area and everything, we can always judge it like the what is the thickness of the deposited layer. But this is very inaccurate. Okay. So because it's inaccurate, what other possible option is to use a ellipsometer. This is a very sophisticated one, and it also measures with 1 nanometer error. So in this case, you can directly get the thickness of the deposited layer through optical or non-contact means. But in some cases, if it's a rougher film, so now as we were saying, this is the best one, right? So if ellipsometer is non-touching your sample or something, so it will be the best one. But the problem with this is, so let's say your film is something like this. Because of what? So anyways, in case of sputtering or in case of thermal evaporation and everything, the film should be like this, right? So there shouldn't be any visible or even like microscopical errors in this. But let's say your surface was like this before, and even with the thermal evaporation or everything, your surface will change to this. So it would have a very high roughness and everything there. So in case of this, so if you are using through ellipsometer, here the thickness would be different, here the thickness would be different. So there would be an uneven, sorry, just a second, yeah. So there would be an uneven measurement, and in those cases, what we use is called a contact based, a contact based thickness measurement technique. So we use a contact based thickness measurement technique. One of the most used one is a profilometer. So in my research as well, I have been using profilometer. So this is the profilometer we have inside our lab, that is a DECTAC XT from Bruker. And so if I can maybe zoom it out, zoom in here, I guess it's a blurry one, but you can see. So this is our, just a second, yeah. So this is the tip of our, sorry, so this is the tip of our probe tip, or this is the basic tip. This touches the, if let's say this is your surface and you have a tip here, this will touch here, and based on that touch, it will drag the tip all over your surface. That's why it's called a contact one. So what it can do is that it can also give you the measurement of the roughness of your film. It can also give you the thickness of your film through these kind of a techniques. Just a second, yeah. So let's say you have a silicon here, you have deposited your silicon dioxide here. So if the tip is here, let's say, if your tip is touching here, there will be a dip here, right? No, so based on not exactly. So based on the material you are using, that's the major problem with the profilometer technique. So it will go there. So this is called a valley type measurement. So this is called a valley type measurement. So there are two different types of measurements, valley and hills. There are several other settings as well, known as the valleys or hills, and so it can measure the thickness, not the thickness, sorry, it can measure the roughness and everything at the same time. But based on hills, you are measuring like this, and based on valleys, you are measuring like this. So there's a valley or there's a hill based on these techniques and everything. So it touches directly. So if you have a very like let's say a organic sample or something like that, or a biodegradable sample, this have a very smoother texture, and because of that profilometry can damage the wafer and everything. So in my cases there have been some damages, but also you need to understand this profilometer tip. Just a second. This profilometer tip is a very costly one. So if you like if it gets damaged, so like you can make a sample again, but the profilometer tip shouldn't get damaged. So this is the proper setup. So this was the PC setup that we have in our lab, and it shows the where the tip goes and the camera setup and everything. So this is the basic setup. You can see. So this is a chuck. This chuck can rotate like this and also like this. So it moves with the x, y, and z axis, and based on that, you have a sample here. I guess you guys can see this. So we have a light, and we have a camera setup and everything, and this is the tip I was saying about. So this tip will directly touch onto it, and there's a software, and based on that we can do everything. So this is a very like zoomed image of my sample. So this is my transistor device, and on that transistor device this tip is directly touching the surface and everything. So what it will do, that it will just scan this much area, like it's a very smaller area, and based on that it will measure the thickness of the layers and everything. So here you can see that there's a blue liquid on top of this, and so it can measure this thickness. So based on your eye and everything, you will see that there's literally no difference between this blue line and the gray line. But when you are touching the sample, or you have the sample in your hands or something, so you can see there's a visibly like thickness difference between these two. But to measure that, we'll need these kind of techniques. So these are in my devices, these are about like 500 to 600 nanometers, and it can measure very fine, but it won't be able to detect like let's say 1 nanometer or 5 nanometer difference that much easily. So because of that, in my cases, what I have been doing is that I have been taking like several different datas from the different positions. Let's say we are putting it here, we are putting it here, like that. And so from 15-20 different datas, we are getting the average out, and based on that we are stating that this is the basic thickness and there's a mean thickness and these kind of things. Apart from this profilometry, there's another way to directly like through the contact method to directly measure this. So this is known as the atomic force microscopy, or AFM. And let me write it, AFM. So this is also another type of characterization techniques as well. So what it does is that it gives you a 2D scan of your surface. So let's say you have a sample like this. You have a sample like this, okay, and this is your surface. Oh, and this is your surface, okay. So what it gives you is that it gives you a 2D scan of the surface. That's it. Now with this 2D scan, what you can do, it you can also convert it to an 3D scan or a 3D image, and based on that you will see a proper valley like structure on top of your substrate like this. You can convert it to a 3D image, and based on this you can always measure your heights, you can always measure your like roughness of the sample. So if you are taking the data for let's say 5 micron by 5 micron region or something like that, so out of this total surface, you won't get the entire surface, okay. So let's say you are taking a smaller, very small area, and based on that, let's say it's a 5 micron by 5 micron area, and based on the surface you can determine what is the roughness of your surface and those things. But our main focus is towards the height measurements. And how does this thing works? The basic understanding of this thing is that, so this is your sample, right? This green one is your sample, and let me write it down. And the sample surface is very rough, but we need to know the thickness of this. So we have a cantilever with a very fine tip. You can see it here. We have a very fine tip and a cantilever attached to it, and we have a laser source. So the laser source will shown directly on the back side of the tip, and it will get deflected directly to an photodiode or a camera sensor. Now with the like arrival of any kind of a valley, or let's say a hill or something like that, based on that, the placement of the tip will be changed. So sometimes it will be like this, sometimes it will be like this, so like this. So based on that, this change in the tip, what will happen is that the intensity and the angle of the light, the laser, would be changed, and based on that there's a feedback mechanism. And this feedback mechanism does what is that it gives directly, it stores the data and it gives directly and feedback to this tip. And it provides the tip to be get, at least it like it doesn't get damaged. The main thing is that it doesn't get damaged. So there are several different methods as well. So like we also have several different kind of operating processes. So the first one is your general one, that is the contact mode. So we have a contact mode, that is the basic thing. Now the with the change of this process, like from the profilometry to this AFM, we also have another one that is called the non-contact mode. Now you can see that in non-contact mode, because it's a direct piezoelectric sensor and cantilever type of a thing, based on that what happens is that the accuracy decreases. And there's another mode that is called the oscillating mode, in which there's a very fine distance between the tip and the surface. So let's say the surface is here. So it's a very fine difference, and based on the feedback mechanism, the distance is maintained at a very fine length and everything. So these are the techniques that can be used to measure the thickness. So atomic force microscopy, profilometer, and your basic ellipsometer and everything. So based on the color you can also decide if what's the thickness of these things and everything. So now we move on to COMSOL multiphysics. So what's the need of a COMSOL multiphysics? So before the first aim was to reduce resource wastage, right? So if you are trying to fabricate some devices and your devices are not performing well, so you need to know what's the reason behind it's not performing well. So you need a a tool or a simulation platform which shows you that why the system or the device is not performing. So so to reduce this kind of a resource wastage and these kind of a things, you need COMSOL multiphysics. So there are basic three major aims of this. So the first aim is, what is the underlying phenomena? If the device is working, what is the underlying phenomena? So if the device is working in a very random way or something like that, you also can let me write it down completely. Explanation. You can explain what is the basic phenomena of how is it working or something like that. The main thing is that prediction. So inside this prediction, this resource wasting comes from. So you have a basic prediction of how this sensor will work and why there's a change in this. So based on this physics based applications and everything, physics based environmental applications and those things. So you can know that why there's a change in this, so if you have a very like your fabricated devices data and if you have a simulated data, so if they are not matching, why there's a mismatch. So based on that you can predict what is the what is the basic case, or what is the basic cause that these two devices are not these two results are not in sync. So this is the basic thing. And the final one is comparison. So for, as I was saying, so what is the comparison? So if there's, let's say, a deviation in performance, so why there's a deviation, and if let's say with a longer duration running of running of these things and everything, so why there's a basic deviation in performance and those things. So you need to know that as well. So based on that, before fabricating the device itself, you need a platform that can simulate the device itself, and it gives a proper explanation why there's a deviation. If there's no deviation, how accurately the device is performing and everything, what is the physics behind it. So these kind of a things can be done through COMSOL multiphysics. So COMSOL multiphysics has different kind of a things. So it can also used on fluids, electromagnetics, heat, structural things, chemical things, acoustics, equations, different kind of optimization. So if you are trying to optimize materials, if you are trying to optimize a specific sensor for a specific use case, you can use this. And it can be also integrate directly with MATLAB codes and those things for CAD purposes and those things as well. And for specific case, you can directly model something. You can directly user interface. So like you can interface your directly through this console platform, and you can get the basic comparison reports and those things as well. So this was the basic thing that have been taught inside this week's class. So I'll have to join, like I am getting a call. Let's have a 5-minute break and I'll join within 5 minutes. So I'll be here anyways. So I'll be starting the class again in 5 minutes. Okay. And if you have any questions, you can ask me after that. Yeah, sorry for this disturbance. Let's start again. Yeah. So let's move on to the questions. If anybody has any questions regarding this, so I'm not going entirely detailed of this COMSOL multiphysics like simulation and everything, because you have guys have already seen the videos and try to do basic exercises directly from the internet itself, and you will get the basic hang of it. And while you are doing your research and everything, so you will get the basic things like how to use it and everything. So I'm not going into details in this basic lecture class. So if anybody have any question, please let me know. Otherwise, then I'll start the question answer session. There's a here somewhere. Just a second, guys. Hmm. Okay, so let's start with the question. So today's first question is silicon dioxide can act as selective mask against diffusion at high temperature. So is it a true statement or a false statement? Is it true or false that silicon dioxide can be, yeah? So if it's true, let me know why it's true. So this is true, obviously. It's true. So my next question is why? I've already discussed it in today's lecture as well. It's an insulation layer. No, so at high temperature, look at this point, right? So we are considering why at high temperature. So check it why it's why it can be used as at a high temperature. That's fine. It's an insulation layer. So there are many insulation layers as well, right? Anybody? Yes, that's perfectly the correct one. So silicon dioxide have a very high melting point. So due to that, it can be used as an selective mask. Okay, let's move on to the next one. Question number two. Now, flow of modeling. So you have to list it down, right? So the first one is make geometry. Two is post process results. 3 is type of study. 4th is add materials. 5 is apply physics conditions. So you have to like tell me which is the first one, which is the second one, and which is the third one, so on. Yeah, please go on. The given answer by 31542 is wrong. So you are saying you should like type of study, right? So no. Yeah, someone was putting up their hands, right?
Sir, make geometry, add
Okay.
materials,
So you are saying making the geometry, right? Then,
add materials,
hmm,
um,
okay,
apply the physical boundary condition,
okay.
post pro and study type of study and post processing result, sir.
So you are saying like this, right?
Yes,
So 1, 4, 1, just a second. 1, 4, 5, 3, 2, right? You are saying that.
yes, sir.
Yeah, that's correct. So why is it like that? Only because first we have to make the geometry that in which kind of a structure do we need and everything, and then we'll move on to the material addition and which kind of a material we are using in this process. Then we'll apply the boundary conditions through physics, and then we'll move on to the which kind of a study do we need, so if we are needing any kind of a specific study or not, and then we'll post process the results. So this is the correct flow. So let me write it down again. One, not this one. Let me write it like this. So let me remove this. So the process would be 1, 4, 5, 3, and 2. Okay, let's move on to the next one. Now move on to the next question. So just a second. Let me turn off this. Yeah. So Miller indices describe the dash of crystal planes. So which one is it? One is phase. Yes, orientation. Orientation or flat. So among this, which one can we get like obtain directly from the Miller indices as well? So do anyone have any idea of that? So like if we can get the orientation, can we get the phase or the flat? Or how do we get that? How do we get that? Orientation is the correct answer. That's fine. Perfectly fine. No, no, no. The follow-up question is that, so if we need to know about the phase of the crystal, how do we know that? Can we directly get it from the orientation itself? Yeah, sure, sure, sure. You can ask it right now. Bharti, you can ask your question right now if you have a request or something. Or you can type it down there as well. So let's move on to the next question, but you can write it down and I'll check it. So are you typing it down? Mm, okay, that's fine. Okay. So tell me the thermal oxidation flow. Okay. So with respect to the thermal oxidation flow and everything, you have to tell me which one is true and which one is false. Okay. Now, this is the first one. So at room temperature, silicon in air creates very thin layer of native oxide. Second, dry oxidation is used for creating thicker oxide layers. Third, wet oxidation is faster than dry oxidation. So among this, which one is true and which one is? Oh, sorry, I missed the one. Yeah, yeah, yeah. Just let me complete this and then I'll go back to that one. Sorry. So room temperature of silicon air creates. This one is true. Okay. So there's a very thin layer of this silicon dioxide created if we keep the silicon wafer directly in open air with a very small heat or something in a humid temperature like in India or something. So there will be a very thin layer of native oxide, that is silicon dioxide. What about the second one? Is it true or false? False. Okay, that's also correct. So with dry oxidation, we can create a very thin layer as well. So what would have been the correct the correct change of this one? So if I need to make this statement as a correct one, yes, perfect. So it can create from 0.05 to 5 micrometer as wet oxidation. So the third one is also true. As wet oxidation is much faster, it's very like cumbersome to control the rate And because of that, what happens is that because of that we can't make a very thin layer of like very thin layer of oxide. And like if let's say we need a very thin layer of oxide of 5 micron or something like that. So with that the major problem is that we can't control the thickness itself, so it will be anyways waste. The second point, already have been mentioned in the chat. So point zero 0.05 to 5 micron thickness it can create very easily. So it's not generally for thicker oxides. It can't make very thin ones. Let me write it down first. So very thin layer. It can't make very thin layers, but it can make up to 0.05 to 5 micron layers. Okay. So as it's calling a thicker layer, so a 0.05 micron is not a thicker layer. So that's why we are saying that. So with dry oxidation we have a very complete control of this, but with wet oxidation and everything there we don't have a very perfect control of that. Do you have any question regarding this question? Anybody has any question? So let me go back to the previous question. Sorry, I missed that like discussion of that question. So in that, what I was asking is that can we get the phase if we have the information of orientation? That was my question. So try to answer this. And not only for silicon, I would say like for any other crystals as well. So is it possible or not? That's my primary question. And if it's possible, so like how do we do this? So like that's the major point. No. We are not using anything apart from the like details of the orientation. That's the like question mainly. So if we have the orientation of the crystal, so we have the basic Miller indices. Can we can we get the phase details of this crystal directly without using any kind of a spectroscopy or those kind of things? I'm just asking. So the answer would be no. So answer would be no, because silicon has a diamond cubic structure, right? So based on that, if I have the details of orientation, so based on that orientation, what do I have? I have the diamond cubic phase, right? So orientation gives the idea of the surface plane. So the surface plane, but it can't translate directly into a phase. So like we have the basic information that it is a diamond cubic phase, but we don't have the entire details of this phase and everything, right? That's the basic thing. So now move on to the next question. Question number, I guess 5, right? Yes, 5. So we have a shape memory alloy, right? We have a shape memory alloy. So it is a type of which kind of a material? Which kind of a material is a shape memory alloy? So we do this, I guess. Which kind of a material is a shape memory alloy? So there are several different kind of like materials and these kind of a things we have learned in the video of console one. So the in the console video about the materials and everything, we have already directly learned about these kind of like alloys and materials. So what kind of a material is shape memory alloy, and what is the basic phenomena it uses to get this? Anybody knows this? Should I give the option? It can retain its shape from stress and after stress. Yeah. Now, you are saying about this shape memory alloy details, but what kind of a material is it? Like, uh, so there are ferroelectric ones and different kind of a things. So what kind of a material is it? The answer is, sorry, just a second. Ferroelastic. Yes, that's the correct answer. Shape memory alloy retains the shape and based on the stress it's given, and so this is a ferroelastic material. So as already have been described in the video itself. Let's move on to the next one. Yeah, you can ask me any question. Yeah, go ahead. Okay, maybe a mistake then. Yeah. So, let me have a look. So I have a basic question. Is there any secondary flat in 111 type, P type silicon wafer? Is there any? Yeah, no. That's the correct one. There is no secondary flat. So this is the one of the most primary ones. Because of that, there's a single primary flat in 111 P type silicon wafer. Okay. Let's move on to the next one. Question number 7. So regarding these kind of wafers as well. So the primary angle between the primary and secondary flat of 100 P type and N type silicon wafers are. So what is the primary angle between these? So for 100 P type and for 100 N type, what is the primary angle? So 90 for P type, right? Let me write it here. So for P type ones, as I have already discussed, there's a 90-degree between these, and for N type, there's a 45-degree gap between these, right? So anybody have any question regarding COMSOL and these things? So if there is no question, I'll move on to this. Let me have a bit. Just a second, guys. Just a second. Yeah, so what was the question? How to export 180? Let me check this. Yeah, so for N type 100, it's 180. Sorry for, yeah, you were correct. So who was it? Yeah, Shabana, your answer was correct. It will be 180. It was my mistake. Yeah. And what was the next question? How can we export data into CSV? So how can I show it to you? I don't have console in like in my this PC. So I have in my labs PC. So the base like the what I do generally is that I get the data directly onto the tables, and from that table you can directly click export and you can get the CSV file. So like how to explain that? Just let me so first you have the derived values, right? So first you have the derived values, and from the derived values, you will go to the results, and you will have the tables, right? From the tables, you have to click export to get the table as an CSV. So was I able to like explain this? I don't have the software right now, so I would not be able to like give you a basic demonstration. Um, I'm not entirely sure what was like the question, like 100 and 111 about that. Shabana, yours one was right. I'm not entirely sure. So, like, anybody has any questions apart from this? Otherwise, we'll end the session here. So, if there are no questions, we'll end the session here.
Sir, I
So,
have one question, sir.
yeah, sure. Go ahead.
Uh, Sir, uh, in, sir, we can make photolithography in dry etching, in wet etching technique by preparing some purchasing component locally. We can
Uh,
try to make not silicon, sir. By we can make some plastic mold or 3D printing structures by using this etching technique to
photolithography.
create. Yes, okay, sir.
Are you saying photolithography or
No, sir, I am saying to photolithography and 3D printing technique, we can make an integrate to this to make the modeling. We can create two technologies combined in together, sir.
hmm,
It's possible or not? I haven't questioned, sir.
okay. So you are saying that with photolithography and while utilizing like etching through locally sourced materials or something like that, right?
Yes, sir.
Maybe it's possible. I haven't tried it obviously, but like maybe it's possible, but I don't think you will get that entire how do I say it? Like the like you need a very detailed structure and everything, right? So I don't think with a local one or something like that it will be possible, because I don't know if you know that because like this PRs and everything, right? So it comes like from outside India, and they export it through like 2 months 3 months like through the boats and through the ships and everything. So till date we are utilizing their material from, and we are exporting that material from US and everything, so to get the higher quality materials and even for using in labs. So if you are using in like let's say in industry or something, you need the utmost quality, right? So you need the best quality, the best performing device and everything. So I don't think it will be possible to get that much. So if you are not going to like, if you are trying to achieve that, maybe it's possible, but you won't get the ultimate results or like the perfect results with that.
Thank you, sir.
Yeah, thank you. So thank you everyone to for attending this session. So we'll start